Okay, so the point of this video is to go through your multiple choice electricity test, and for each question how to find the solution and to give you some tips about the best way of doing these types of questions. I'll be answering the questions in decreasing order of how many people got the question wrong. So those that come first are the ones that were answered wrong most often. Question 23 was the question which was answered wrong by the largest number of people. Effectively, it's a question about EMF and the difference between EMF and the terminal potential for a cell or a battery. So the battery is marked 9.0 volts, and this means it has an EMF of 9, which means that every coulomb of charge that passes through the battery gains 9 joules of energy, but also loses a little energy in the cell's internal resistance. However, the cell's internal resistance and the cell itself is part of the whole circuit. And so A is the correct answer because the whole circuit, including the internal resistance of the cell, gets this 9 joules of energy. That means that B is wrong because the external circuit doesn't get those 9 joules of energy because a small part of it is lost in the cell's internal resistance. The PD across any component connected to the battery will be 9 volts. It just can't be right because this component might be connected in series. And there isn't 9 volts across the battery if a current is flowing because of the internal resistance and the lost volts by the internal resistance. So that's why A is the answer. This is a question about circuit rules and whether you understand about the behaviour of a thermistor at different temperatures. So the important thing here is that the temperature of the thermistor decreases. And we know that a temperature of a thermistor will affect its resistance. And because when you give it extra energy, it makes it conduct more easily. If the temperature of the thermistor decreases, its resistance increases. So R increases as the temperature goes down. What we're trying to find out now is what happens to the current in the two branches when this happens. What we know is that this has no significant internal resistance, and that means that the potential difference across the thermistor and the potential difference across the fixed resistor won't change. And we know because they're in parallel with each other, the potential difference across the two will be the same. If the resistance of the thermistor increases, but the potential difference of the thermistor across the thermistor stays the same, then just using Ohm's law, V equals I times R, I equals V over R, V stays the same, R goes up, I goes down. For this resistor, the potential difference stays the same, and whatever happens here has no effect whatsoever on the current flowing through this resistor. The potential difference between here and here will not be affected by what happens in this branch. And so R stays the same, V stays the same, I stays the same. So in A1, the resistance increases and so the current decreases. In A2, the resistance stays the same, the voltage stays the same, the current stays the same. So current decreases, current stays the same. The answer is A. So this question also not very well answered. Probably I think because you have to think intelligently about which formulae apply to which part of the question. So we're told that this power line transfers 800 megawatts when the potential difference across it is 132 kilovolts. Which means that we can apply the fundamental definitions of power and potential difference and current. And so power is current times voltage, or current is equal to power divided by voltage. That means the current in this cable is going to be the power, which is 800 times 10 to the 6, divided by the voltage, which is 132 times 10 to the 3. And this gives us the surprisingly big answer of 6,060 amps. So we know that that's the current flowing through. We also know that the power, the energy which is lost at a power of 800 megawatts divided by 100. So we can use the formula that tells us about Joule heating, P equals I squared R here, to find out what the resistance is. R equals P over I squared, which is now 8, not 800, times 10 to the 6. That's megawatts, divided by 6.06 times 10 to the 3 squared for I squared, and that gives us a value for R, which is pretty close to being 0.2 ohms. The answer is A. Question 19, a question about fundamental units. In order to do this, we're going to use Ohm's law again, which is equivalent to the ohm. Well, R equals V over I. So the units that are equivalent to the ohm are going to be the units for potential difference divided by the units for current. Potential difference is measured in joules per coulomb, and current is measured in coulombs per second. And so that's equal to joules, coulombs to the minus 1, times coulombs to the minus 1, seconds to the minus 1 to the minus 1, which is seconds. So that gives us joules, coulombs to the minus 2, seconds, which is B. So this question really is just a question manipulating formulas. We need to use the resistivity formula combined with Ohm's law, R equals V over I. And when we take this and combine it with the resistivity formula on the datasheet, rho equals RA over L, we can substitute an expression for R to give us rho equals V over I times A over L. And this comes out to be rho equals VA over IL. And this is answer B. Another way to look at this though is in terms of units. If we know that the unit of resistivity is ohm meters, we can look at the answer and see that V over I, which is resistance in ohms, is then multiplied by the units of A divided by the units of L, which is meters squared divided by meters, giving us ohm meters, which is the correct unit. This next question is a relatively simple one. We know that the thermistor's resistance changes depending on temperature, and this NTC, negative temperature coefficient means that as the temperature increases, the resistance decreases. And this rules out both A and B. The decision of whether or not the answer is C and D depends upon the realization that it's not a linear relationship. And as the temperature increases, the resistance decreases, but the resistance never goes to zero. In the case of D, you can extrapolate that if this carried on, by the time you got to 90 degrees, then it would have become a superconductor. So the answer has to be C. Question 24. We just need to remember from GCSE for the first part that as the voltage increases, the current increases, the resistance of the filament lamp increases, and so the filament lamp has to be P. For a semiconductor diode, the current only passes in one direction, and then only after the potential difference has increased beyond somewhere around 0.6 volts. That means that the graph for the diode is R. Combination of P and R is answer A. For question 11, one of the key things here is that the internal resistance of the cell is negligible, and that means that the potential difference across the cell is equal to its EMF, and the potential difference between the two ends of the combined pair of resistors is also going to be constant. If we increase the intensity of light on the LDR, its resistance decreases. Since this fixed resistor stays the same, we have the same voltage over now a smaller resistance, combined resistance. And that means the current and the ammeter reading will increase. The answer is either C or D. Because the current through this resistor increases though, and its resistance has stayed the same, then the potential difference across this resistor, the fixed resistor, will have increased. But remember, the circuit rule says that these two potential differences have to equal the potential difference across the cell, which hasn't changed. And that means that this potential difference will have to decrease in order for them still to add up to V. So it's not C, it's D. We can approach this in a couple of ways, but I think the simplest way is to say that if rho equals RA over L, then the resistance is given by rho L over A. And this is the situation for the shorter, thinner wire. We can expand this a little bit to give us rho L over pi R squared. Now for the other wire, R2, that's equal to rho times 2L, because the wire is twice as long, divided by pi times 2R all squared. And this turns out to be rho L times 2 divided by pi R squared times 4. But this rho L over pi R squared is just R. So it's R times 2 over 4, which is R divided by 2. So if you have a component, let's say for instance a resistor, and you need to measure the potential difference across it, you need to connect to both ends of the resistor in order for you to be able to detect the difference in potential. This means that if you have a resistor which has a finite resistance, then the only way to stop some of the current going through the voltmeter is for the voltmeter ideally to have an infinite resistance. And so the answer is C. Okay, so with this one we can start first by thinking that the number of particles which pass a point in a minute is the particles having a charge of 2e will divide into the total amount of charge to give you the number of particles. If we want to expand that using what we know about the total amount of charge, then we can change it to the current times the time divided by this 2e, these doubly charged ions, and that means that we get n is equal to 0.64, which is the current, times 60, the total number of seconds, because the time has to be in seconds, divided by twice the charge on an electron, 1.6 times 10 to the minus 19 coulombs. And this gives you C. Now actually D is an interesting answer, because if you put your numbers into the calculator in the wrong order, forget to take account of things like brackets, then D is one of the answers that you get. To make this question a little bit easier, imagine that the cell has a potential difference of 12 volts. And because these three resistors are the same, and because TP has to have a potential difference of 12 volts because of the circuit rules, it's in parallel with the cell, these three resistors will have the same current, the same resistance, so the same voltage. And because there are three of them, those three same voltages all have to be 4 volts. The same is true for the top branch. And so if this is 12 volts, then we can start to think about not potential differences, but potentials at points. The potential at point S is 12 minus 4 is 8 volts. The potential at point Q is 8 minus 4 is 4 volts. And the potential at P is 0 volts because it's directly connected to here. And the potential at T is 12 volts because it's directly connected to here. Same here, and here, and here, and here. Now, in order to decide whether or not the resistor will read 0, we just have to compare the potentials at the 2 points. And the only pair of points here which have the same potential are Q and U. Both of them 4 volts, so the answer is A. So starting with the datasheet equation, we have rho equals R A over L, or R equals rho L over A, rho L over pi d over 2 squared. For resistor X, where D is not the same but is half as much, this means that the value of resistor X's resistance is 4 times as much. This 2 gets squared and goes up to the top. And this gives us then the combined resistance is R plus 4R is 5 times the resistance. Answer D. So from the data sheet, we have the equation P equals I squared times R. R is a constant because it's a component which obeys Ohm's law. So P is equal to K times I squared. This is a square relationship, which is a parabola, which the answer is A. C is a proportional relationship, P equals Ki, and D is an inversely proportional, where P is K over I, and this is something like P equals P naught minus IR. So now we come to the Atlantic torpedo. I don't know if the fish was named after the weapon or the weapon was named after the fish. One of the useful things here is that we're told that all of this happens in 1 second, and then we're asked for the power output. So really, all we're doing is calculating the energy, because the energy in 1 second is the same as the power. So we can use our energy is defined as charge times potential difference, and that means that energy is current times time times potential difference, E equals ITV. And we can work out the energy in a single pulse using that simple equation. E equals ITV, which is 15 amps times 2.0 times 10 to the minus 3 seconds times 220 volts. And that's the energy produced by a single pulse. The energy produced in a second is just going to be 200 times that. And if you add that up, you find that that gives you 1.32 times 10 to the 3 watts, which is B. So I've added a little dotted line here to show that once the potential difference across the semiconductor diode goes above 0.6 volts, then it doesn't really resist the flow of current, and so the current becomes proportional to the potential difference, which is more than that. The answer to this can't be B or D, because no current will flow if the potential difference is below that 0.6 volts across the diode. And it can't be C, because once it is bigger than that, then there will be some current flowing. The resistance isn't infinite for any potential difference. So the answer is A. Actually, this is the kind of question which is easier as a multiple choice than it would be as an extended response question, because deriving the shape and working out the shape of that graph from scratch would have been quite difficult to do. If you put two cells in parallel with each other, then the charges can only pass through one cell or the other, and so the potential difference between these 2 points that I've labelled X and Y is only due to one cell or the other. And since each cell has an EMF of 3 volts and no significant internal resistance, then the potential difference between X and Y is going to be 3 volts. So the answer is either A or B. And then really we just have to apply Ohm's law. We know that this is 12 ohms and we know that this is 3 volts, and so we can work out the current. I equals V over R, which is 3 over 12, which is 0.25 amps. 3 volts, 0.25 amps, no, 25 amps. The answer is A. So this is a question about percentage uncertainties and how you combine them to give an uncertainty in your final measurement, the final conclusion. For resistivity then, we have our equation from the data sheet, rho equals RA over L. And since we're not actually measuring R, but we're measuring V and I, we need to then make that equation an equation with V and I in it, times A over L. But we're not measuring A either, we're measuring the diameter. And so we have rho equals V over I times pi d over 2 squared over L. And if we take out the constants from this, we get an equation rho is equal to pi by 4 times V d squared over I L. In each one of these terms then makes a contribution to the uncertainty in our value of resistivity. And in fact, the percentage uncertainty in the resistivity is equal to percentage uncertainty in the voltage plus twice the percentage uncertainty in the diameter plus the percentage uncertainty in the current plus the percentage uncertainty in the length. And because of this square, the only one which is doubled is the diameter. And so that's the one that makes the largest contribution. Since all of those percentages are equal, this is the biggest factor. So the number of electrons is going to be the total charge divided by the amount of charge per electron. We know that there are electrons, and we know that the total charge is the current times the time, and the thing to remember is that this is 2 minutes. This gives us N is equal to 20 times 10 to the minus 3 milliamps times 2 times 60 divided by 1.6 times 10 to the minus 19, which is the number of coulombs for a single electron, the charge on a single electron, and that gives us answer B. Okay, question 10 is about superconductors. When a material becomes a superconductor, its resistance is almost zero. This is the distractor. The resistance of a superconductor is absolutely totally zero. This one is correct. This is the right answer. The PD across the superconductor when it passes a current is zero because it has no resistance, and nothing is a superconductor at room temperature. Now this is a question about measuring resistivity, calculating resistivity from measurements. So we have again the formula ρ equals RA over L, but we don't have resistance, we have current and voltage, so we substitute from Ohm's law. Ρ equals V over I times A over L. In that case we have ρ is equal to 0.2 times 5.0 times 10 to the 8 divided by 0.4, the current, times 1.5, the length in meters. And this gives us an answer of 1.7 times 10 to the minus 8. Actually, we don't need a calculator for this really, because we have 0.2 over 0.4, which is 2. So it's 5 divided by 3 times 10 to the 8. I think the most intelligent way of approaching this question is to start out by working out what the unit for energy is, because we know that will tell us about D, it will tell us about C, because potential difference is energy per unit charge, and it will tell us about B because that's energy per second. So if we use energy, it's the same as work, which is force times distance, and we know that force is mass times acceleration, then energy is mass times acceleration times distance. That means 1 joule is equal to a kilogram times a meter per second squared times a meter. So the unit of energy is kilograms, meters squared, seconds to the minus 2. That means this one is wrong because it has seconds to the minus 1. If we now apply this to power, a watt is a kilogram meter squared, seconds to the minus 2 per second. This gives us kilograms meters squared, seconds to the minus 3, which means that that unit is correct. Now, since only one of you got this question wrong, I'm going to leave it at that. Now, everybody got this question right, but just in case you were guessing, I'm going to go through this quickly. What we have then is that energy over power equals time, and energy is charge times potential difference, and so the time we want is Q times V over P, and that's 9,400 times 3.7 divided by 200 times 10 to the minus 3. Now that would give us the time in seconds, but since we want the time in hours, I'm going to divide that by 3,600. If I do that, I get 48.3 hours, which is B. For question 22, you were quite sneakily given a piece of information that you didn't need, because all we want to know is how many electrons pass through a given cross-section. And we're told also that the time is 1 second, so in fact we don't even need to worry too much about the time. The number of charge carriers is equal to the total charge divided by the charge for each one of them. We know that the total charge is the current times the time, but this is just 1, and so the total number of carriers is just the current divided by the charge on a single electron, and that's equal to 10 divided by 1.6 times 10 to the minus 19 coulombs, and that's C, 6.3 times 10 to the plus 19 carriers.